Equipped with his five senses, man explores the universe around him and calls the adventure science. Edwin Hubble said that in 1948, and it fits this search with unusual precision. Because our first difficulty is not that the Milky Way is too small to find, but that it is too large, too surrounding, and too full of dust for us to see as a whole. We cannot fly far outside our galaxy and take the kind of portrait we can take of Andromeda or Triangulum. We are inside the Milky Way's disk, embedded among its stars and gas, looking through the structure we are trying to understand. NASA's own astronomy materials state this plainly. We can only take pictures of the Milky Way from inside the galaxy, so our sense of its full shape has to be built from clues rather than from a single direct photograph. That changes the entire emotional geometry of the problem. Imagine waking up in a city so vast that every road, every tower, every neighborhood surrounds you in all directions, while a thick haze blocks the long view. You can see streetlights nearby. You can follow traffic. You can listen for distant trains. You can trace the pattern of buildings one district at a time, but you cannot rise above the city and look down on the full map. That is our situation inside the Milky Way. Human beings have looked up at the pale band across the night sky for thousands of years, yet for most of that time we did not know whether it was a cloud, a river of fire, a seam in the heavens, or the combined light of countless faraway stars. Even after telescopes improved, the larger problem remained. A galaxy is easiest to understand from the outside. Home is the one galaxy we do not get to leave. So our galactic address has never been read from a signpost. It has been reconstructed, bit by bit, star by star, motion by motion. Astronomers learned to use the sky the way a surveyor uses landmarks after fog has covered the horizon. They charted star fields. They measured how stars shift position against more distant backgrounds. They studied how fast gas clouds move through the disk. They listened to radio signals from hydrogen, because hydrogen is spread across the galaxy in enormous quantities and can reveal structure that visible light conceals. They used infrared observations because infrared light can pass through dust more effectively than ordinary visible light, exposing regions that would otherwise remain buried behind dark lanes. That is why mapping the Milky Way is not a single discovery. It is a long forensic reconstruction assembled from many kinds of evidence that agree, overlap, and correct one another. ESA explains that Gaia has now made more than 3 trillion observations of about 2 billion stars, building an extraordinarily precise three-dimensional map from within the galaxy itself. That effort is one of the clearest signs that the map of home has been earned through measurement, not guessed from imagination. And the need for so many methods comes from the Milky Way's own material. Dust sounds harmless until astronomy forces the word to become physical. Interstellar dust is not like a thin decorative veil. It is a real obstacle. Tiny grains of carbon-rich and silicate-rich material scatter and absorb visible light, especially along the dense plane of the galaxy where stars, gas clouds, and star-forming regions are concentrated. When we look toward the inner Milky Way in visible wavelengths, large portions of that view are dimmed, blurred, or blocked altogether. This is one reason our galactic address stayed uncertain for so long. Distance matters, yes. Scale matters, yes. But dust is the element that turns a broad, luminous system into a maze of partial glimpses. Infrared astronomy changed that. NASA's James Webb Space Telescope and earlier infrared missions can peer through many dusty regions that once looked nearly opaque, revealing stars and structures hidden behind them. That does not mean the fog vanishes completely. It means the map becomes less fictional and more physical. This is why the modern effort to understand our place in the Milky Way feels less like receiving a final answer and more like sharpening a once blurred image. The older view of our galaxy was assembled from fragments, and many of those fragments were good. Astronomers already knew before James Webb that the Milky Way is a spiral galaxy with a central bar, a wide stellar disk, and a complicated inner region crowded with stars, gas, and dust. NASA describes it as a spiral galaxy about 100,000 light-years across. But knowing the broad form of the city is not the same as knowing the district, the street, and the local traffic around your own building. New instruments do not always replace the old map. Often they test it, tighten it, and reveal which regions were oversimplified. That is exactly why infrared observations matter so much. They do not merely add prettier images. They let astronomers inspect the parts of the Milky Way that visible light left incomplete, and there is something almost sobering in that. We often speak as if humanity knows where it lives in the cosmos with perfect confidence. We can name the planet, the solar system, the galaxy, even the local group. But each level of that address has taken labor to establish. Earth circles the sun belongs to the Milky Way. The Milky Way sits among other galaxies. Each statement sounds settled now, but every one of them had to be proved against older assumptions. Edwin Hubble himself helped overturn the belief that the Milky Way was the whole universe by showing that Andromeda lay far beyond it. A century later, the work has become more intimate. We are no longer only asking whether other galaxies exist. We are trying to determine where, within our own, the Sun actually resides, how that region moves, and what kind of galactic environment shaped the history of our world. That is where the modern map of home becomes more than a diagram. It becomes a condition of life. A star does not live in abstraction. It lives in an environment. The density of nearby stars, the frequency of violent events, the thickness of gas clouds, the local magnetic conditions, the amount of dust, the movement through spiral structure, all of these belong to the setting in which a planetary system forms and survives. So when astronomers work out our galactic address, they are not filling in a decorative blank. They are identifying the larger environment of the Sun, and therefore of Earth. They are asking what kind of neighborhood this really is, whether it is crowded or sparse, harsh or comparatively stable, ordinary or unexpectedly favorable. The map matters because location has consequences. The methods behind that map are beautiful in a practical way. Gaia measures parallaxes and motions with astonishing precision. Radio astronomy traces gas that optical telescopes cannot follow cleanly through dust. Infrared observatories pull hidden stellar nurseries and crowded inner galaxy regions into view. Together, these methods do something no single photograph could do. They let us infer the architecture of the Milky Way from the inside out. The process is patient. It relies on repeated observations, cross-checking, and better instruments. ESA notes that Gaia's measurements include motions, luminosities, temperatures, and compositions for billions of objects. NASA highlights how infrared views can uncover stars and structures behind dusty clouds. What emerges from all of that is not romance. It is navigation, a civilization inside a galaxy, slowly learning to read its own address. So when someone asks, "Where are we in the Milky Way?" the honest answer begins not with a coordinate, but with a limitation. We are in the strange position of trying to map the building while standing in one of its hallways. We do not get the luxury of distance. We do not get the clean outside portrait. We work with star maps, radio surveys, infrared imaging, distance measurements, stellar motions, and the accumulated discipline of many generations of astronomy. That is why the search has taken so long, and that is why each improvement matters. Every sharper infrared image, every more precise stellar motion, every better model of the galaxy's structure pushes our address from approximation toward reality. If this journey has given you something worth carrying into the rest of the night, thank you for spending this time here. A like or a soft tap on subscribe is a real source of encouragement for me to keep making these long science stories. And if you feel like sharing, I would love to know where you are listening from and what time of day or night this found you. Your thoughts and suggestions help me shape these episodes with more care each time. And even after the larger map begins to sharpen, one detail remains unexpectedly modest. Our solar system does not appear to sit in one of the Milky Way's grandest celebrated lanes, but in a smaller structure whose name many people have never heard. That smaller structure has a name, and it changes the way most people picture our place in the Milky Way. The Sun is not thought to sit in one of the galaxy's largest, most dominant spiral arms. NASA describes our location as the Orion Arm, also called the Orion Spur, a small partial arm lying between the Sagittarius and Perseus arms. In other words, the solar system is not riding the brightest main lane of the galaxy at all. We live in a narrower branch, a kind of secondary structure inside the larger spiral pattern. That correction matters because the common mental picture is usually far grander than the measured one. Many people imagine that if the Milky Way is a great spiral city of stars, then surely our Sun must sit on one of its great luminous boulevards, somewhere important, somewhere architecturally central, somewhere with a view that feels worthy of a civilization capable of naming galaxies. But the evidence points somewhere more modest. NASA's graphics place the Sun in what they call a finger of the Orion Spur, not in the galactic center and not in one of the best-known major arms. ESA's Gaia work has reinforced a broader lesson here. Even the spiral structure of the Milky Way is more complicated and less tidy than older textbook pictures suggested. There is something valuable in that loss of prestige. Astronomy has a long habit of removing us from imagined places of honor. Earth is not the center of the solar system. The Sun is not the center of the galaxy. And now, even within the Milky Way, our address appears less like a flagship district and more like a smaller connecting region between larger stellar structures. Yet, this does not make our location less interesting. It may make it more physically revealing. NASA notes again and again that the Orion Spur is a small partial arm, and that wording matters because it tells us the Sun's neighborhood is real enough to define, but not so dominant that it controls the galaxy's large-scale appearance. We belong to a local structure inside something much larger. The names around us help make the geometry clearer. On one side lies the Sagittarius arm, and on the other, the Perseus arm. These are larger, more widely recognized spiral features of the Milky Way. The Orion Spur sits between them, linking local regions rather than standing as one of the galaxy's giant star-making lanes. Older maps sometimes treated the spiral pattern differently, and more recent data have refined that picture, but across NASA sources, the location of the Sun remains consistent, near a small arm segment or spur between Sagittarius and Perseus. That is the correction worth holding on to. The solar system is not in the grand center of the map, and not in one of its most celebrated star-filled avenues, but in a smaller branch whose importance is local rather than majestic. And local does not mean unimportant. In science, modest positions often turn out to be physically favorable ones. A smaller spur can still contain rich star-forming history, clouds of gas and dust, clusters, and the long-term stability needed for planetary systems to persist. ESA's Gaia observations of stellar nurseries in our surrounding region show that the solar system sits within a mapped three-dimensional environment of nearby star-forming structures extending thousands of light-years around us. That does not prove the Orion Spur is uniquely ideal, but it does show that our neighborhood is part of a real, measurable galactic setting rather than a blank gap between important places. The branch may be smaller, but it is not empty. This is where the emotional balance changes. The truth is humbling, but not diminishing. A smaller branch means our position is not prestigious in the ceremonial sense. It does not place the sun on a galactic throne, but it may place us in a region where extreme crowding is lower, where the surrounding stellar environment is less violent than the deep inner galaxy, and where long spans of orbital stability were more likely to survive. That possibility becomes more interesting when placed beside the fact that life on Earth required extraordinary stretches of continuity. The Orion Spur may sound minor on a diagram, yet minor structures can still provide major consequences. There is also a deeper lesson in the name itself. Orion Spur sounds temporary, almost incidental, as if our location were a side road branching off the larger galactic system. In one sense, that is close to the truth. NASA and JPL have both described the Sun as residing in a spur to an arm, or a minor arm, called Orion. That language strips away the old instinct to imagine home as architecturally privileged. It asks for a more mature view. The Milky Way is not arranged around us. We simply occupy one workable place within it, one address among many, one environment whose significance comes not from grandeur, but from consequences. So the picture becomes a little clearer. We are not living in one of the Milky Way's great bright arms, but in a smaller branch between larger structures. And from there, it becomes natural to look at one more part of our address, how far this quiet region lies from the galaxy's crowded center, and why that distance may matter more than it first seems. The measured distance is about 26,000 light-years. NASA gives that figure repeatedly in its Milky Way material, describing the solar system as lying about 8 kiloparsecs from the galactic center, or about 26,000 light-years. The Milky Way itself is commonly described by NASA as about 100,000 light-years across, which means a radius of about 50,000 light-years from center to outer edge. Put those two numbers together, and the result is surprisingly plain. We are not near the center, and we are not close to the rim. We are somewhere in between, in the broad middle part of the stellar disk. That middle position is easy to miss because the galactic center has such a strong pull on the imagination. The center sounds like the place where everything important must happen. In one sense, that instinct is not wrong. The inner Milky Way is crowded, bright, and dynamically intense. Sagittarius, a star, the supermassive black hole at the core of our galaxy, lies more than 26,000 light-years away from Earth, and the surrounding region contains dense concentrations of stars, gas, dust, and energetic activity. But that is exactly why our own address is so revealing. We are far enough out that the core is not part of our daily stellar environment, yet close enough to remain clearly within the main body of the galaxy. This is where the Milky Way begins to feel less like a symbol and more like a place with neighborhoods. If the full disk stretches roughly 50,000 light-years from the center in each direction, Then our position at 26,000 light-years places us in what could almost be called a middle suburb of the galaxy, not the downtown core, not the rural outskirts, somewhere in the long inhabited spread between. That framing is not just stylistic, it is physically useful. It tells us that the Sun formed and evolved in a region that belongs fully to the galactic disk, but is not immersed in the most congested inner environment. And that middle distance helps explain why our local view of the Milky Way looks the way it does. We are inside the disk, looking along and across its dusty structure rather than standing above it. From here, the galactic center appears in one direction as a heavily obscured, star-rich region, while other directions open toward thinner parts of the disk and eventually toward the outer galaxy. The number 26,000 light-years is not just a number on a chart. It sets the perspective from which every human being has ever seen the Milky Way. It is part of the reason our galaxy appears to us as a band across the sky, rather than as the clean spiral shape we so easily draw in diagrams. There is also a quieter consequence in that distance. A location farther from the crowded center can mean lower stellar density than the innermost bulge, fewer close stellar encounters, and a different balance of radiation, gas, and gravitational disturbance over long spans of time. That does not mean our region is empty or uniquely protected. It means that location inside a galaxy is never trivial. 26,000 light-years is not merely where we are. It is part of the background condition under which the solar system had time to remain stable for billions of years. Later, when astronomers speak about galactic habitability, this middle distance becomes one of the first details worth remembering. Another detail sharpens the scale even further. NASA notes that the Sun, together with Earth and the rest of the solar system, takes about 250 million years to complete one orbit around the galactic center. So our address is not fixed in the ordinary sense. It is more like a long path through a city so large that one circuit takes longer than complex life has existed on Earth. But even within that motion, the average distance still tells us something stable about our place in the Milky Way's architecture. We belong to the disk, about halfway out, in a region that is neither central nor peripheral. That is why this part of the map matters so much. It removes two misleading pictures at once. We are not living close to the brilliant, crowded heart of the Milky Way, and we are not living at some remote edge where the galaxy has almost run out. We are in a middle zone, inside a smaller spur, orbiting within a system large enough to make even 26,000 light-years feel local. Once that scale settles into place, another detail begins to matter more than before, because the view of our address changes again when we ask what new instruments actually added to this map, and whether James Webb truly discovered where we are, or simply revealed our home with sharper depth. By this point, the map sounds almost settled. We know the solar system is in the Orion Spur, and we know it sits about 26,000 light-years from the galactic center. So it is fair to stop here and be very honest about what James Webb did and what it did not do. Webb did not suddenly discover our galactic address from nothing. That address had already been built over many decades from star counts, radio astronomy, distance measurements, infrared surveys, and orbital modeling. What Webb changed was the sharpness, depth, and realism of that picture in some of the Milky Way's most obscured regions. It made parts of the galaxy less guessed and more directly examined. That distinction matters because the claim can easily be overstated. If someone says, James Webb found where we are in the Milky Way, the sentence sounds dramatic, but it compresses too much history into one moment. Astronomers already knew the broad architecture of our galaxy before Webb launched. They already knew the Milky Way has a barred spiral structure, that the Sun is far from the center, and that dust is one of the main reasons the inner galaxy is so difficult to study clearly. Webb's real contribution is subtler and, in some ways, more powerful. Its infrared instruments can look through dust far better than visible light telescopes, and its sensitivity and resolution allow astronomers to inspect dense, star-forming regions of the inner Milky Way with a level of detail that earlier observations could not match. That is exactly why Samuel Crow's line is so useful here. He said, "There's never been any infrared data on this region with the level of resolution and sensitivity we get with Webb." That sentence does not mean the region was unknown. It means the region had never been seen this well in infrared. Webb was not writing the first rough version of the map. It was tightening the map where dust, crowding, and limited resolution had left major uncertainties. In other words, Webb did not replace the long work of galactic cartography. It strengthened it by opening parts of the Milky Way that had remained physically difficult to inspect. The example that makes this clearest is Sagittarius C, a star-forming region near the galaxy's center. In November 2023, NASA reported that Webb's near-infrared camera captured a roughly 50 light-year-wide portion of this dense central region, about 300 light-years from Sagittarius A star, the Milky Way's central supermassive black hole. The image contained an estimated 500,000 stars, along with protostars, infrared dark clouds, ionized hydrogen, and long, thin filament-like structures that astronomers are still trying to understand. That kind of view does not simply look impressive. It changes what researchers can test about star formation under extreme galactic conditions. And that is where Webb's value becomes concrete. A broad map tells you where the district is. A much sharper infrared view tells you what is actually happening inside the district. In Sagittarius C, Webb revealed clusters of stars still forming, outflows from young objects, dense clouds so thick that stars behind them disappear even to Webb, and extended ionized gas structures that suggest intense local activity. These are not decorative details. They are the physical contents of the inner Milky Way. They help astronomers ask whether star formation near the galactic center behaves differently from star formation farther out in the spiral arms, and whether the central environment changes the balance of gas, turbulence, radiation, and magnetic effects. So when people speak about Webb and our place in the galaxy, the most accurate version is this: Webb did not hand humanity a new cosmic address card. It gave astronomers a better look into the dusty, crowded environments that make that address meaningful. It improved the realism of the setting. It revealed hidden structure inside the parts of the Milky Way that had resisted clean observation. It showed not just where the inner galaxy is, but what kinds of physical processes are unfolding there. That is a quieter claim than a sudden discovery headline, but it is also stronger because it stays close to what the telescope actually did. If Webb made the inner Milky Way more visible by working in infrared, then the next thing worth looking at is the obstacle that made that necessary in the first place. Because much of our confusion about home was caused not by distance alone, but by the dust spread through the galaxy's own disk. In many parts of astronomy, distance is the first suspect. A thing looks faint, so we assume it is simply too far away. But inside the Milky Way, another problem sits much closer to us. The galaxy is threaded with interstellar dust, and that dust changes what visible light can do. NASA's infrared astronomy explainers describe the basic effect very directly. Dust absorbs ultraviolet and visible light, and then re-emits that energy in the infrared. In ordinary visible images, dusty regions often appear as dark gaps or heavy lanes, not because nothing is there, but because the starlight behind them has been blocked or scattered before it could reach us. That is why the Milky Way can mislead the eye. We live inside a galaxy filled with stars, gas, and dust, yet large parts of its disk do not present themselves cleanly in visible light. Toward the galactic center, this becomes especially serious. ESA's Hubble material on the central Milky Way states that the galactic core is obscured in visible light by intervening dust clouds, while infrared light can penetrate that dust much more effectively. The same point appears again in ESA's description of observations towards Sagittarius A star. Many objects in the central region are hidden at visible wavelengths by thick clouds of dust in the galaxy's disk, so astronomers turn to infrared vision to understand what is really there. Once you hold that mechanism in mind, the mystery becomes more physical and less abstract. Dust is not just a poetic inconvenience or a vague haze. It is made of tiny solid grains mixed into the interstellar medium. Those grains interact strongly with shorter wavelengths of light, especially visible and ultraviolet light. So, when starlight from the far side of a dusty region tries to cross the Milky Way's disk, part of that light is absorbed and part is scattered out of the line of sight. The result is a damaged view. Structures disappear, star counts look incomplete, bright regions become patchy. Dark lanes appear where stars and gas may still be abundant. NASA's description of the spiral galaxy, NGC 1566, makes the same principle vivid in a different setting. In Hubble's visible view, dark regions are where starlight is absorbed by dust, while Webb's infrared view reveals the dust and structures in a completely different way. This is exactly why infrared astronomy matters so much for the Milky Way. Infrared light is not magic, and it does not pass through every cloud without limit, but it can get through dusty regions far more effectively than visible light. NASA's Spitzer and Webb materials repeat this point across many star-forming regions. Interstellar dust blocks, visible light, while infrared observations can penetrate dust clouds and reveal what lies within or behind them. In W51, one of the Milky Way's major star-forming regions, NASA notes that visible light is blocked by dust, but the region is revealed in infrared. In the Carina Nebula, NASA explains that Webb revealed emerging stellar nurseries and individual stars completely hidden in visible light pictures because of its sensitivity to infrared light. That is why Webb can uncover stars, protostars, and buried structure in places that once looked almost blank or hopelessly dark. NASA's Webb science pages explain that stars form in molecular clouds seeded with dust grains, and that Webb's near- and mid-infrared instruments allow researchers to identify materials and stars within these dusty clouds much more effectively. Webb's ability to work at these wavelengths is one of the main reasons it has transformed views of star formation. It is not merely seeing farther, it is seeing through. And that phrase matters. Seeing through does not mean dust stops mattering. In many Webb images, some clouds remain so dense that they still appear dark. NASA's release on Sagittarius C notes that even Webb cannot fully penetrate certain infrared dark clouds there. But that partial access is already enough to change the map. Once some of the buried stars, young stellar objects, gas structures, and ionized regions become visible, the Milky Way stops looking like a silhouette and starts looking like a working physical system. There is another layer to this that makes dust even more important. Dust is not only an obstacle, it is also part of the environments where stars and planets form. ESA notes that dust grains throughout the Milky Way absorb starlight and then radiate that energy in the infrared. NASA's Webb star formation explainers say that molecular clouds are seeded with dust grains, elements, and molecules that may later become part of stars or remain in surrounding material where planets eventually form. So the same material that hides part of the galaxy from our eyes is also part of the raw substance from which new systems emerge. Dust conceals, but dust also builds. That changes the emotional balance of the problem. The obstacle is not empty darkness. It is active matter. The reason our place in the Milky Way stayed hard to see is that we are looking through the same galaxy that is still making stars. The disk is not a clean, transparent sheet. It is full of ingredients, debris, clouds, and recycled material from older generations of stars. When we point a visible light telescope toward dense regions of the galaxy, especially inward toward the center, we are trying to look through a workshop while the work is still going on. Infrared astronomy does not remove the workshop. It lets us see deeper into it. So yes, dust is one of the real reasons we never saw our place clearly. Not the only reason, because scale, geometry, and our position inside the disk all matter too. But dust is the mechanism that turns those difficulties into something tangible. It blocks visible light, scatters detail, reshapes the apparent brightness of regions, and hides objects that infrared instruments can later reveal. Once that mechanism is understood, the next view into the Milky Way's center feels less mysterious and more earned, because then we are ready to look at what Webb actually found near Sagittarius C when those dusty layers began to give way. Once dust becomes part of the explanation, the view near the Milky Way's center changes completely. The darkness is no longer empty. It is a screen hiding an active environment. And when James Webb looked into Sagittarius C, it did not find a simple cluster or a neat patch of stars. It revealed a crowded, turbulent region near the heart of the galaxy with a level of detail that earlier infrared data had not reached. NASA says Sagittarius C lies about 300 light-years from Sagittarius A star, the Milky Way's central supermassive black hole, and that Webb's image captured this region in unprecedented detail, including features astronomers had not seen before. The scale of the image is part of what gives it force. The full NIRCam view covers a region about 50 light-years wide, and in that single frame, astronomers estimate that roughly 500,000 stars are visible. That number matters because it turns the galactic center from a distant concept into a measurable environment packed with structure. This was not a sparse field with a few bright markers. It was a dense inner galaxy scene filled almost to excess. ESA's Webb release describes exactly that, a 50 light-year wide portion of the Milky Way's dense center containing an estimated 500,000 stars, along with features that were still unidentified when the image was released. What Webb saw there was not just quantity, but variety. NASA reported protostars in the region, meaning stars still in the process of forming. It also identified infrared dark clouds, so dense that even infrared light struggles to pass through them, along with a large region of ionized hydrogen glowing under the influence of radiation from young massive stars. In that ionized gas, astronomers also found long, thin, filamentary or needle-like structures whose origin was not yet fully understood. So the image did not simply show more stars. It showed a working environment where star birth, radiation, dense clouds, and unresolved structures all coexist in the same harsh central setting. That is why Jonathan Tan's remark carries so much weight here. He said, "The galactic center is the most extreme environment in our Milky Way galaxy." NASA's release gives the fuller idea. This is an environment where current theories of star formation can be tested under especially severe conditions. That is the deeper significance of Sagittarius C. Astronomers are not only admiring a dramatic picture, they are using Webb's data to ask whether stars form differently near the galactic center than they do in calmer parts of the Milky Way, where gas density, magnetic fields, turbulence, and radiation may be less intense. And that is where the observational drama becomes scientific leverage. A region like Sagittarius C sits close enough to the galaxy's core to feel the effects of one of the Milky Way's most demanding environments. Yet it is also close enough for Webb to resolve individual structures within it. Samuel Crow's statement from NASA's release makes that point especially clear. There had never been infrared data on this region with Webb's level of resolution and sensitivity. In other words, Sagittarius C was known before, but Webb changed how well it could be studied. It turned a difficult inner galaxy zone into a place where astronomers could inspect protostars, cloud boundaries, ionized gas, and unresolved filaments with much greater confidence. There is also something important in what Webb still could not fully do. Some of the darkest clouds in Sagittarius C remain opaque even in infrared, which tells us the region is not merely dusty, but in places extremely dense. That detail matters because it keeps the image honest. Webb did not erase every obstacle. It pushed deeper into the galactic center than visible light could manage, and deep enough to reveal a far richer physical scene, but it also showed where the limits still are. The Milky Way's center is not just hidden, it is genuinely difficult terrain. So the answer is not that Webb found one spectacular object near the center of the galaxy. It found an entire environment in sharper form, hundreds of thousands of stars, young stars still assembling, thick dark clouds, glowing hydrogen, and strange filaments that do not yet fit neatly into a finished explanation. That is what makes Sagittarius C so compelling. It is not one discovery standing alone. It is a dense physical scene that reveals how much of the inner Milky Way had remained blurred until infrared observations reached this level. And once that inner region comes into view, our own location starts to feel different by comparison. Because if the galaxy's center is this crowded, magnetized, dusty, and active, then the quieter part of the Milky Way, where the Sun lives, begins to look less ordinary, and perhaps more fortunate. NASA's Webb team described the galactic center as the most extreme environment in our Milky Way galaxy, which is a careful way of saying that conditions there are not like the solar system's local surroundings. Near the center of the Milky Way, stars are packed more tightly together, dense clouds of gas and dust are common, and the environment is shaped by stronger gravitational crowding and more energetic activity than what we experience in the Sun's neighborhood. NASA's astrobiology program put this idea plainly years ago. Being farther out in the galaxy helps protect the solar system from the strong gravitational effects of stars clustered near the galactic center, effects that could disturb distant comet reservoirs such as the Oort cloud. That does not mean astronomers can simply stamp one region safe and another region unsafe. The honest version is more measured. What researchers often discuss is a galactic habitable zone, not a sharp ring with a hard boundary, but the broader idea that some parts of a galaxy may be more favorable than others for long-term planetary stability and complex chemistry. NASA's astrobiology material explains that regions too close to the center may suffer from stronger gravitational disturbance and harsher conditions, while regions too far out may have had fewer of the heavy elements needed to build rocky planets. That is what makes the solar system's position so interesting. We are not in the dense inner core, and we are not far out in the sparse outermost reaches. We sit in the disk, in the Orion Spur, at a distance from the center that may have offered a useful balance. Enough generations of earlier stars to enrich the region with heavy elements, but enough separation from the crowded core to reduce some of the worst gravitational and radiative stresses. That is not a guarantee of life. It is a description of a neighborhood that may have been more accommodating than the galaxy's central districts. Once you see it that way, Earth's story begins to widen. Life on this planet may depend not only on the Sun being the kind of star it is, but also on where that star spent its history inside the Milky Way. A stable planetary system requires time. It requires material. It requires long stretches during which orbits are not violently disrupted. The galactic center, with its dense stellar crowding and extreme physical conditions, is a more difficult setting in which to preserve that kind of continuity. Our local region is not empty or inactive, but compared with the inner Milky Way, it appears far less severe. There is also a useful emotional correction here. In the earlier parts, our location sounded modest because it was not central and not prestigious, but modest can carry a hidden advantage. A smaller branch of a spiral galaxy, well away from the brightest and most crowded inner environment, may be exactly the kind of place where a planetary system can keep its balance long enough for oceans, atmospheres, and biology to persist. The Sun's neighborhood does not look impressive in the ceremonial sense. It looks workable in the physical sense. That is why the map of the Milky Way stops being just a map. Once astronomers connect location with consequences, our galactic address becomes part of the explanation for why Earth had time to become Earth. The Sun's place in the Orion Spur, far from the galaxy's most crowded core, may not be glamorous, but it may have been one of the quiet conditions that made everything else possible. And that picture changes again when we stop treating our location as fixed, because this neighborhood is not standing still at all. The whole solar system is moving through the Milky Way at tremendous speed. NASA gives the number very clearly. Our solar system orbits the center of the Milky Way at about 515,000 miles per hour, or about 828,000 kilometers per hour, and it takes about 230 million years to complete one full orbit around the galactic center. That means our address is real, but it is not static. It is a moving address, carried along a path so large that one lap takes longer than the time since the first dinosaurs appeared on Earth. That changes the meaning of location. When people imagine an address, they usually imagine a fixed pin on a map, something parked and settled. But the solar system does not live that way. The Sun, the planets, the asteroids, the comets, and the distant icy bodies bound to the Sun are all traveling together around the Milky Way's center. So when we say we are in the Orion Spur, about 26,000 light-years from the core, that is true in the large structural sense, but within that structure we are always in motion. This is why astronomers sometimes speak of a galactic year. A human year is the time Earth needs to circle the Sun once. A galactic year is the time the solar system needs to circle the Milky Way once. NASA's number, about 230 million years, makes the scale feel almost unfamiliar. During just one galactic orbit, continents drift, species appear and vanish, mountains rise and wear down, and entire chapters of Earth's biological history come and go. By that clock, human civilization has existed for only the thinnest fraction of a single turn. And that motion is not visually obvious to us because everything around us shares it. Earth goes around the Sun and its system go around the Milky Way. The Milky Way itself moves through the larger universe. But because we are carried along inside these motions, they do not feel like speed in the ordinary sense. There is no cosmic wind pressing against us, no blur outside the window. The motion is real, but it is gravitational motion, not motion against a road. That is one reason the Milky Way can seem so still in the sky, even while the solar system is moving through it at hundreds of thousands of miles per hour. There is another consequence hidden inside that speed. If our home is always moving, then the environment of the solar system is part of a longer galactic history. Over immense spans of time, the Sun does not remain beside exactly the same stars, in exactly the same local conditions, forever. It continues along its orbit through the disk, through the broader architecture of the Milky Way. So our location is best understood in two ways at once. We occupy a certain region of the galaxy, and we travel through that region as part of a much larger orbital pattern. That also makes the earlier idea of a favorable neighborhood more interesting. It is not only that the solar system formed in a quieter part of the galaxy than the crowded inner core. It is also that this quieter position belongs to a moving orbit with its own long-term history. Earth's story unfolded while the Sun was circling the Milky Way, carrying the entire planetary system through the galaxy year after year, age after age. The map is not a still image. It is a path. So the Milky Way is not just the place where we are. It is the larger system through which we are continuously traveling. And once that becomes part of the picture, another part of the story becomes easier to appreciate because a galaxy is a very difficult thing to map from the inside when your own observation point is moving with it, surrounded by dust and buried among billions of stars. That is the real reason the Milky Way took so long to chart with confidence. We are not looking at it from a clean external distance. We are inside the disk, trying to reconstruct a structure that wraps around us, while dust blocks visible light, and our own solar system moves through the very system we are studying. So the map of the Milky Way did not come from one photograph or one telescope. It had to be assembled the way a long investigation is assembled, by collecting many kinds of evidence and fitting them together until the larger pattern became hard to deny. The most important modern detective in that story is Gaia. ESA says Gaia has made more than 3 trillion observations of about 2 billion stars and other objects, building an extraordinarily precise 3-dimensional view of the Milky Way by measuring positions, motions, brightness, temperature, and composition. ESA also notes that this survey reaches almost 2 billion stars, about 1% of the total number of stars in our galaxy. That number is striking because it sounds both enormous and incomplete at the same time. 2 billion stars are enough to redraw our sense of the galaxy, and yet they are still only a small fraction of the whole Milky Way. That is why mapping the galaxy feels less like sketching a simple outline and more like solving a case with many overlapping clues. Gaia is powerful because it measures stars one by one, which means the map is built from individual distances and motions rather than from a distant photograph alone. ESA's own Milky Way materials say Gaia maps our galaxy from within, gathering information star by star. From that, astronomers can reconstruct spiral structure, stellar streams, the shape of the disk, and the past motions that reveal how the Milky Way grew over time. The map becomes not just a picture of where stars are, but a record of how they move and how the galaxy has changed. But Gaia is not the whole story, because Gaia does not erase dust, and the Milky Way does not become transparent simply because one mission is precise. Some regions, especially toward the inner galaxy, remain difficult because dust and crowding make them harder to study cleanly in visible wavelengths. That is where James Webb enters the effort. Webb does not replace Gaia. It complements Gaia by revealing structures and star-forming environments that remain hidden or blurred in other data. NASA's releases on the Milky Way's center make this very clear. Webb's infrared sensitivity lets astronomers see through dusty regions and inspect places such as Sagittarius C with a level of detail that earlier infrared data had not reached. So the modern map of the Milky Way is really a collaboration between methods. Gaia provides the broad three-dimensional stellar census and motion field. Radio observations trace gas across the disk. Infrared missions, including Webb, reveal buried structures inside dusty regions. Each wavelength fills in what another leaves uncertain. That is why the story took so long. The galaxy we live inside is not merely large. It hides parts of itself in different ways, and astronomers had to learn how to read each kind of hiding. Vera Rubin once said, "The most important feature of any telescope is the imagination with which it is used." Carnegie Science attributes that line to a 1993 address later published in Bright Galaxies, Dark Matters. It fits this problem exactly. A telescope does not hand over the Milky Way in finished form. Someone has to decide what to measure, what wavelength to use, what kind of motion matters, what dark gap may actually hide a rich structure, and how to combine one mission's strengths with another's limits. The progress came not from one perfect instrument, but from using many instruments in a more intelligent way. So the answer to why it took so long is not that the Milky Way was beyond human reach. It is that the galaxy had to be mapped from the inside, star by star, motion by motion, wavelength by wavelength. We had to infer the city while living in one of its neighborhoods. And now that the map has become far sharper, one final change begins to matter more than the coordinates themselves, because once James Webb helps show us where we are, the meaning of that address begins to turn inward. And now, the map stops being only a scientific achievement and starts becoming something more personal. By the time James Webb enters this story, it is no longer telling us that Earth is special in the old, central, privileged sense. In fact, it does almost the opposite. It places us more clearly inside an ordinary physical setting, a solar system in the Orion Spur, inside a barred spiral galaxy, moving around the Milky Way at about 515,000 miles per hour, in a structure shaped by dust, gravity, star formation, and time. NASA states those points plainly. Our solar system is in a small partial arm between the Sagittarius and Perseus arms, and it belongs to a barred spiral galaxy rather than some isolated, simple island of stars. That could have felt diminishing. It could have reduced us to a minor detail in a very large machine, but the strange thing is that the clearer the address becomes, the more intimate it begins to feel. A vague universe can remain abstract. A mapped universe becomes a place. Once we know that the Sun is not near the center, not in one of the Milky Way's grandest arms, and not fixed in place, but carried along a 230 million-year orbit, home starts to look less like a symbol and more like a real location inside a real system. That is part of what Webb changes. It does not merely improve an image, it restores context. It shows that our address in the galaxy is not a label pasted onto a blank background. The Milky Way is full of physical processes that continue whether or not we are watching them. Dark clouds thick with dust, young stars still forming, gas lit by radiation, inner regions crowded by hundreds of thousands of stars, and structures so dense that even infrared light cannot pass cleanly through them. When Webb revealed Sagittarius C near the galaxy's center in far greater detail, it did more than sharpen a picture. It reminded us that the galaxy around us is active, layered, and unfinished. We are not living in a static diagram. We are living inside an evolving environment. And that is why the meaning of this map becomes warmer, not colder. The Milky Way is not arranged for our comfort. The solar system is not in a place of ceremony. The Orion Spur is a minor structure. The Sun is one star among vast numbers. But when the address is reconstructed carefully, one measured fact at a time, a different kind of significance appears. This world exists in a region of the galaxy where stars had already lived and died, where heavy elements had already been made, where a long-lived star could form with planets around it, and where enough stability may have held for life to continue long enough to become aware of its surroundings. The map does not flatter us, it explains us. Carl Sagan captured that feeling in one of his most enduring lines. Because the cosmos is also within us, we're made of stuff. We are a way for the cosmos to know itself. The wording appears in his cosmos narration. If this journey has kept you company for a little while tonight, thank you for staying here with me until the end. I'm truly grateful for your time, your presence, and the care you bring to these long explorations. And if this episode gave you something meaningful to carry with you, a gentle like or a quiet tap on subscribe would mean a great deal to me, because that support gives me the encouragement to keep making these slow science stories, one by one. If you'd like, you can also share where you are listening from, or what part of the world this found you in tonight. I always love seeing how far these stories travel, and I'm equally grateful for any thoughts or suggestions you'd like to leave behind, because they help me improve each next video with more care. Wherever you are, I hope the rest of your night is peaceful, your thoughts grow lighter, and your sleep comes easily. Thank you again for being here. And until next time, take good care.